All right. So, as you may be aware, there's been a lot of exciting black hole news this year, and this is the second of our Black Hole Month presentation series. So, Dr. Jerry Dunifer, Professor Emeritus of WSU Physics and Astronomy, has visited almost all of the telescopes he's going to talk about tonight. He's visited all the telescopes he's going to talk about tonight, many of which were part of the actual Event Horizon Telescope. And Planetarium coordinator and doctoral candidate in physics and astronomy, Ben Coughenour, is going to discuss the findings of the Event Horizon Telescope and further go into that. His research focus is on the astrophysics of compact objects, which include black holes. So.
He's also my boss.
And he's Jeff's boss, so be nice to him. So without further ado, I give you the black holes.
Ben is also a student of Ed Kakat, who
wonderful.
Speak here frequently. So good evening, everybody. So on April 10th, about 10 weeks ago, there were 7 simultaneous press conferences held around the world in 7 different countries, in different languages, held in places like Washington, D.C., Tokyo, Shanghai, Santiago, and so forth. And the purpose of the press conference was to announce to the world that for the first time, astronomers had obtained a picture of a black hole out in space. So the telescope that they used to get this is known as the Event Horizon Telescope. It is not a single telescope, but it's actually 8 pre-existing radial telescopes that have been linked together to function as a single telescope. So this is the picture which you probably have all seen, and Ben will be going into considerable detail explaining what you see in this picture. I'll just mention that this is in a galaxy M87, which is 55 million light years from Earth. And the black hole that generates this image has a mass of 6.5 billion times the mass of our sun. So this is the one and only formula which I will show you this evening. This tells you the angular resolution of a telescope. Resolution refers to the smallest angle at which you can see some detail when you're looking at the image of some object. And the equation tells us that the angular resolution is given by approximately 1.22 times the ratio of lambda over d, where lambda is the wavelength of the light or the electromagnetic wave which is being used, and d is the diameter of the telescope. Now that photograph I showed you in the previous slide required very high resolution, down to about 20 micro arc seconds. That's 20 millionths of 1 arc second, with there being 3,600 arc seconds and 1 degree. So in order to get that kind of resolution, one has to make this ratio, lambda over d, as small as possible. So you do that by making lambda small and d large. So for that picture, they selected the wavelength to be 1.3 millimeters. So now we're dealing with millimeter waves. This is the type of radiation they scan you with at the airports. And they want to make d as large as possible, and they've made it approximately the diameter of the Earth. Now they have not built a single telescope that diameter, but by linking a number of telescopes together, spread out across the Earth, they can make them function as a single telescope with an effective diameter equal to that of the Earth. So this shows you where some of those telescopes are. For example, Hawaii, Arizona, Mexico, down in Chile, Spain, South Pole, and so forth. Now, there's one problem with millimeter waves, and that is they are strongly absorbed by water vapor in the atmosphere. And so the telescopes have to be in a region where we have a dry climate, and they tend to be at very high altitudes. So So the telescope can be above most of the water vapor in the air. Because the wavelength of the radiation, 1.3 millimeters, is very small for a radio telescope, one has to have the parabolic reflector machined very precisely, and it has to be smooth on a scale of microns. That is maybe a couple 10,000ths of an inch or so. And so most radio telescopes don't satisfy those two requirements. And so these are very specialized radio telescopes which have been used. So, 8 telescopes were used, and I've listed the components here. There was ALMA, the Atacama Large Millimeter and Submillimetre Array, which is located on the Coughenour Plateau in Chile. There is APEX, which is the Atacama Pathfinder experiment, which is sitting right next to ALMA. There is the IRAM 30-meter telescope, which is at the summit of Pico Valletta in Spain. The James Clerk Maxwell telescope near the summit of Mauna Kea in Hawaii. The Large Millimeter telescope in Mexico. The Submillimetre Array back on Mauna Kea, again in Hawaii. The Submillimetre telescope on Mount Graham in Arizona. And finally, the South Pole telescope down at the geographic South Pole.
Is that the one you went to?
Say again?
That's where you were at, also the South Pole?
Yes. I've been to all of these, or near all of these with the exception of 2. The ones I haven't been to are IM in Spain and the Large Millimeter telescope in Mexico. I was thinking of going to see this one, but my surgeon friend that I do quite a bit of traveling with, and who is Hispanic and speaks Spanish, and is somewhat familiar with Mexico, advised me not to do it, said it was too dangerous, too much crime in the area, and the banditos down there. And in fact, I read not too long ago in some articles that the astronomers that go down there in the U.S. have had some problems, like carjackings and things like that. So those are the 2 I have not been to. So we're going to take a look at these individually. First of all, ALMA, which is about 16,600 feet above mean sea level, 23 degrees south latitude. So this is a large flat plain, which you can see here, on which an array of radio telescopes has been set up. Very high, more than 3 miles above sea level. This is a picture of some of the dishes that you see arrayed. There are 66 individual dishes. Some are 12 meters, some are 7 meters in diameter. And first light refers to the first time that scientific data was taken using the telescopes. So I'm going to be giving you the diameters in meters. If you'd like those in feet.
Can they move?
Oh yes, they move them. They move. When they want to look in a very small region with high resolution, they move them far apart. And then when they want to see a larger region of the sky, they move them closer together.
Yeah, and giant treads or something?
I think they know that. I think they pick them up. They've got a mover, which picks them up in literally a giant truck with 2 diesel motors in it. Then it takes them to a new place. It takes some time to move them around. So these
Not a snapshot. Not a snapshot.
No, not at all. So if you want the diameters in feet, you need to multiply the numbers by 3.3. So for example, 12 meters times 3 is 36. And if you add another 10%, that gets you up to close to 40 feet in diameter. So 12 meters, 40 feet in diameter. Apex, 16,700 feet, sitting right next to ALMA. This is a picture of telescope at night. In this case, it is a single dish, 12 meters in diameter. Moving over to Spain. This is the one that was shown on my first slide, the IRAM 30-meter telescope. IRAM is an acronym for the Institute of Radio Astronomy, millimetric. Pico Valletta, Spain, 9,400 feet above sea level, down in the southern part of Spain, close to the Mediterranean. So this one, if you multiply by 3.3, you get just about 100 feet in diameter. This is the second largest millimeter wave telescope in the world. Another picture, sticking up above the clouds. And close up picture, again 100 feet in diameter. Okay, moving on to Hawaii. This is the James Clerk Maxwell Telescope, 13,400 feet above sea level. This is the housing for that telescope right here. There's also the Caltech Submillimetre Observatory, which is here, which was not involved in that photograph. And this is an array. We'll come back and look at it a little bit later. Just another view, the Caltech Submillimetre Observatory and the James Clerk Maxwell Observatory. I worked at Bell Labs for about 2.5 years, and for 2 of those years, I worked with Tom Phillips, who became the director of this observatory. And so I've had a couple rather in-depth tours of that particular one. So this is what the observatory looks like when it's open and taking data. There is a membrane which is stretched over the front usually, which is transparent to millimeter wave and sub-millimeter waves, but reflects both visible light and the near infrared. This is a single dish. It's 15 meters in diameter. This is what it looks like inside the membrane. You're seeing really the back of the reflector and the support mechanism. And this is what it looks like from the front when that membrane is not there. Moving on to Mexico. The large millimeter telescope, Alfonso Serrano, is named for it because he played a major role in getting the telescope built and placed at that location. 15,200 feet above sea level at the summit of Sierra Negra, an extinct, hopefully, volcano. So here it is up at the summit. And another view, a more distant mountain in the back. So this is the location of that telescope. It's about a 4-hour drive from Mexico City. Large millimeter telescope. And a few close-ups of the telescope. This is the largest fully steerable millimeter wave telescope in the world. 50 meters in diameter. Picture at night with some stars in the background. The Submillimetre Array. Well, this is an array of 8 dishes, which you see here. And over here in the background again is the James Clerk Maxwell Telescope. Again, 13,400 feet above sea level on Mauna Kea. Again, they can move these dishes around to get varying resolutions depending on what they are looking at. So here they are packed reasonably close together. And here they're spread somewhat further apart for higher resolution. So there's a total of 8 dishes. They're 6 meters in diameter, the Submillimetre Array. And this is what the dishes look like up close compared to a people size. Okay, going to Arizona. Submillimetre telescope at Mount Graham, about 10,500 feet above sea level. So this is a single dish. It is 10 meters in diameter, and there are actually 3 observatories in close proximity to each other. So this is the Submillimetre telescope here. Off to the right, you see a large building. This houses a large binocular telescope. And just out of view to the left is the Vatican Observatory, which unfortunately doesn't show up in this picture. Another view. And then finally going down to the South Pole. The geographic South Pole, 9,300 feet above sea level. And this is the active part of the dish right here. And in the background is another radio telescope called BICEP 3, which is looking at the cosmic background radiation. Another view of the South Pole Telescope, 10 meters in diameter. South Pole Telescope, BICEP 3, and this is the Keck Array, an array of detectors, again looking at the cosmic background radiation. Another view. It's literally very cool. When I was down there, the temperature was minus 25. This was the middle of summer. This is the longest days of the year. Minus 25, and a little windy, and the wind chill factor was about minus 40. So here's a view at night. Showing a bit of the Milky Way in the background and some of the southern lights, which are quite visible at times from the South Pole. Yes?
On those, on the telescopes that were at the higher altitudes, 15,000, 16,000 feet.
Yes.
What was the breathing like? You get up that high, the breathing's difficult.
When I went to Alma, they wouldn't let us go up to the 16,600 feet because people tend to get hypoxia and die.
Right.
If they have lived down there sea level, you can work at that altitude if you get acclimatized to it gradually.
Okay.
But if you're coming up from near sea level,
Right.
it can be lethal. So we were a few miles away, not quite there.
Okay, that's what and the other thing, the one facility in the South Pole, normally when you build, like on the South, you put pressure on ice or anything, just the pressure starts causing it to sink. Do you know how they solve that problem?
I haven't heard of any problems of them sinking. One problem they have is they get a little snow there each year, and the snow tends to blow around and gradually bury them. But I'm not aware they're actually
Yeah,
sinking
because in
into
some
the
of those
ice.
facilities, they had to have a kind of a continuous jack-up mechanism.
Yeah,
Because the
yeah.
facilities, yeah.
That's right. Yeah, the large center where most of the astronomers and other scientists work is on hydraulic jacks.
Yeah.
And they can jack it up gradually as snow accumulates. Here you can see it's up on pillars, so that the hope is that the snow mostly blows underneath and doesn't pile up. Okay, well, those are the 8 telescopes that were used, and they're in the process now of adding 3 more telescopes to increase the resolution for further studies. There's going to be one in Greenland, the Greenland telescope, which is going to be put up on the highest point on the ice sheet there at 10,600 feet above sea level. That's going to be a single dish, 12 meters in diameter. At Kitt Peak in Arizona, they're going to be using one of the telescopes there. It's there now, but it hasn't been connected to the system yet. It's a 12-meter telescope, 6,300 feet above sea level. And then finally, there is NOEMA Observatory, which is in the French Alps. This is a Northern Extended Millimeter Array, again operated by IRAM, 8,400 feet above sea level, and it consists of 10 separate antennas with a diameter of 15 meters each. Okay, well that is my contribution, and so Ben now is going to take over and go into much more detail than I have, explaining the significance of that photo and what it all means. Okay.
Okay, so photographing a black hole is, oh yeah, sorry, I should move over here, shouldn't I? Photographing a black hole is, this is the photograph. I see some people dressed a little bit better than I did for it today with the actual t-shirt, which I now realize I have to get one of those, which is pretty awesome. But this is the photograph. I'm sure many of you, if not all of you, have already seen it. And just as a quick refresher, it was April 10th, 2019 that the press conferences were held. I watched the one in Washington, D.C., put on by the National Science Foundation, but of course they were all over the world in a variety of different languages as well. Pretty much every member that Jerry mentioned had their own press conference going on in one way or another. Was 7 press conferences in total. If you didn't happen to watch one of those press conferences, you might have maybe seen it in the news.
Once or
And
twice.
I love news headlines because you can get, BBC just telling you exactly what happened, for example, or the New York Times being a little bit more artsy, darkness visible finally, okay. And then CBS, all of its dark glory. I'm not sure what that is supposed to mean, and I'm not sure I want to know, but maybe it attracted more headlines, or that headline maybe attracted more viewers. So what sort of headline you end up getting with a science story is always sort of a fun twist. If you don't happen to read the news, but happen to maybe go to other sources on the internet, you probably would have heard about it there too. We had our nice fun Google Doodle that I thought did a pretty good justice to the image itself. And there were also a lot of people that had fun with the image online as well, whether they're fans of The Lion King and they imagined Mufasa telling Simba to follow his destiny. Or maybe some people just got hungry when they saw the image. Certainly can't blame them. Or my personal favorite as a Lord of the Rings fan, along with being an astronomer, was maybe Sauron saw a relative, which is pretty great. But to understand sort of what this is, what it means, how we got here, we get to sort of go back and talk about what's a black hole and why is it cool or interesting that we got to take a picture of one finally. So I'm sure many of you are very well familiar with at least some of the different definitions we have for a black hole, but maybe the most useful one is an object which its gravity is so great that light, the cosmic speed limit, the fastest thing you have, won't be able to escape. And sort of talk about sort of what it means to escape, we can talk about escape velocity and what that means. As far as people coming up with the idea for a black hole, way back, just about 100 years after Isaac Newton put out his universal law of gravitation, lots of other physicists and astronomers had fun with that. It was John Mitchell who first sort of imagined, or at least wrote down, his imagining of a star which was so massive that light itself would not be able to escape. He didn't really fully understand how light works. It was sort of the corpuscular idea of light, sort of like a light particle throwing a baseball into the air really, really, really quickly. But that was at least the idea. He called it a dark star, and other people had similar ideas since then. To talk about what it means to escape, we can look at escape velocity. And this brings to mind sort of the famous Newton ball cannon experiment when it comes to going into orbit or escaping a body like the Earth. If you were to imagine a very, very tall mountain and you had some sort of cannon on the top of that mountain, if you were to fire a projectile off of your perch at the very lofty top of that mountain, well, if it's sort of just like a normal cannon, that projectile will fall almost immediately right back down towards the Earth. But let's say you fire that projectile, that bullet, a little bit faster. Then it will travel some distance before it eventually falls back down towards the Earth. Of course, it will eventually fall back down towards the Earth, but as you can see, the curvature of the projectile itself is getting closer and closer to the actual curvature of the Earth. And you can imagine firing a projectile fast enough that it stays at the same height above the Earth, where its curvature as it falls due to gravity follows the curvature of the Earth, and it would come right back around and you could catch it if you were accurate enough. Or if there wasn't something like an atmosphere to slow it down and get in your way. Or you could fire it even faster than that. You could get out into an elliptical orbit out around the Earth, which is how many of our satellites work today. Coming yet again back to where you were. But even still, you're being dominated by Earth's gravity. And so when we talk about escape velocity, we mean something much, much faster than that. If you fire an object off of your mountaintop cannon fast enough, it simply won't come back. It'll continue onwards further and further away, slowing down because it still does feel the influence of Earth's gravity, even as it goes towards infinity, but it won't ever actually start coming back towards you. And that's what we mean by escape velocity, to actually escape sort of the gravitational pull. Again, you're still feeling that gravity, but you won't be influenced to come back towards the Earth. And when we send things out like the Voyager probes, we beat the escape velocity for the Earth. It turns out it's not an impossible thing to do. Here's another sort of imagining or diagram of that Newton's cannonball experiment. Fire something fast enough and it leaves. Well, let's say we wanted to go really, really, really fast. You could look at what it would take to leave the gravity of certain other bodies in our solar system. Earth, it's about 25,000 miles per hour that you have to launch something out for it to not fall into orbit around the Earth, but actually to leave Earth behind. Venus is about the same. If you look at this equation over here, the escape velocity, that sort of limit that you have to beat to be able to go out and experience the rest of the universe, it depends on the mass of the object you're escaping and the radius of the object you're escaping, or the radius you're launching from. So the heavier an object is, the faster you have to go, and it turns out the larger an object is, as long as it's not gaining more mass, the slower you have to go. So a smaller object and a heavy object will mean that your escape velocity goes up. So Earth, Venus, roughly the same size, roughly the same density, we get about the same. It'd be a lot easier to explore our solar system if we were launching off of Mercury or Mars, or say our moon. But when you look at the gas giants, despite being much larger in size, you know, if the radius goes up, that escape velocity should go down. They're also, however, much, much, much more heavy and able to make up for that. So you get some outrageous escape velocities. It's a good thing we're not trying to launch satellites off of Jupiter, even if you had a solid surface to launch off of. Coming back to sort of what it means to be a black hole and how we think of black holes today, well, it wouldn't be possible without that man named Einstein, who put out general relativity in 1915. It was not even a year, several months after that, that another physicist came up with our first inkling of a real black hole as we think about them today. But main key point of general relativity, the way that gravity works, rather than just being this spooky action at a distance, is that when you have a mass, it influences the space-time around it, that warps space-time, and any body that travels by is just moving through that curvature of space-time. So as the Earth goes in orbit around the Sun, we're not moving in a circle, the Earth is just moving along in its perfectly normal path, but given the warping of space-time due to the Sun, that produces an orbit. There's our fun two-dimensional way to think about that warping of space-time, sort of if you imagine dropping a bowling ball on a trampoline. Of course, that's not how space-time really is. It's three-dimensional, or four-dimensional if you think about the time. I don't encourage anybody to try and imagine that. It hurts my brain to try. Maybe if you're better at visuals than I am, you can go for it. I like my happy trampoline at least. But as I said, it was less than a year later where Carl Schwarzschild calculated using Einstein's field equations, calculated the solutions for what space-time should look like if you have a point mass or a spherical mass. And he noticed that he got some solutions that would go towards infinity. And he didn't really know what those meant, and he didn't really know, decide how it would matter. We now realize today, though, that when you get those solutions going towards infinity, it would happen at a particular radius away from that point mass or that massive sphere. Particularly, it would depend on the mass of the sphere and the speed of light here. We call that the Schwarzschild Radius, and that's sort of how we think of the event horizon. If we look back at our escape velocity, and sorry, Jerry only showed you one equation, I'm showing you lots of equations, so I apologize for that. But if you look at our escape velocity equation, it might not be so hard to sort of work our way back towards the Schwarzschild radius. If you change the escape velocity to c, the speed of light, and then square everything, and then do a little bit of rearranging, lo and behold, your capital R turns into the Schwarzschild radius, meaning the Schwarzschild radius for any object is the radius at which the speed of light is no longer fast enough to escape that body. And it's kind of fun to think about. It turns out every object has a Schwarzschild radius. For most everyday things, that's very, very, very small. So if you took the Earth and you squeezed the entire mass of the Earth inside of a sphere of radius 9 millimeters, that would mean the Earth became a black hole, because launching a beam of light off that radius, it wouldn't be allowed to escape. Jupiter is quite a bit heavier than the Earth, so it would be a larger black hole, about 3 meters in radius. The Sun, 3 kilometers if you brought the Sun down to a black hole. And then here are some fun ones that are actual real black holes that people like to study and people like to talk about. Cygnus X1 was one of the first candidate black holes ever seen in the sky using X-ray telescopes. And it would have roughly, given its mass, the best mass measurements we have today, roughly around 10 solar masses, would give it a Schwarzschild radius about 44 kilometers. That's more real size, I would say. Sagittarius A star, the supermassive black hole at the center of our own Milky Way galaxy. We're getting into much larger numbers, 12 million kilometers, but that's still tiny compared to, say, the size of our solar system, about 8% the Earth-Sun distance. M87, we're going to talk about a lot today, would have a Schwarzschild radius of about 128 astronomical units. So that's huge. That black hole is bigger than our solar system. M87, as it turns out, is a pretty monstrous black hole as well. The next thing is, how do we detect a black hole? If we can think about black holes as just squeezing a whole bunch of mass into a tiny little area, well, how would you see them? If light doesn't escape, how would you know? We don't really directly see black holes until just now, but we'll talk about what that means. But the way we detect black holes, and we've been studying black holes, is by looking at how they interact with their environment. And there's a number of different ways we can do this. This is the fun sort of, it's gravitationally lensing and warping the light coming from a distant galaxy. Gravitational lensing is one of the ways we can detect mass, not necessarily black holes directly. It's more likely that when we detect black holes, they're sort of being naughty, maybe like cannibalizing their partner star. And that's certainly the case of Cygnus X1, which is in what we call a high-mass X-ray binary. It's eating the outer envelope of its neighbor star. As that material falls off of the neighbor star, it forms a disk around the black hole, which we call an accretion disk. Sometimes you'll even have jets launched in either direction away from the black hole above or below that disk. But as that material falls in, you get an extreme friction. That material starts moving at relativistic speeds. It gets so hot that it shines in the X-rays, which is why the first time we started seeing objects that we thought would be black holes was using X-ray telescopes and wondering why you would have this really bright X-ray source suddenly coming out from you at the sky. Cygnus X1 is one of the most well-studied black holes. It is a stellar mass black hole. It was formed after the death of a very heavy star, so maybe, like I said, 10 times the mass of our sun. But there's a whole other different breed of black holes. And we've sort of think there's one, or are confident there's one at the center of our own Milky Way galaxy. And if I play this video without skipping to the next slide, hopefully, one of the ways we know that there's a supermassive black hole at the center of our Milky Way galaxy is by tracking the positions of stars very near the center of our Milky Way. And we see these stars orbiting around what looks like a blank point in the sky, that sort of star shape at the center, very much in the same way that comets orbit around our sun. Just by doing the Newtonian math, you can look at the orbits of those stars and calculate what must be at that center. And the weight, the gravity that you would need would be about 4 million times the mass of our sun. But it's in a very, very, very tiny area, and we don't see it really emitting most kinds of light. So you have something very, very heavy, very, very small, and these stars are orbiting it. So that would be a supermassive black hole, and we're pretty confident there's one in almost every major or normal-sized galaxy. Sometimes they're a lot easier to find than just by tracking the stars near the center of a galaxy, and M87 is maybe the best case of this. This is a giant elliptical galaxy with a huge sort of jet coming out of it, or a beam of highly energized particles. And that jet, it's believed, what could cause these particles to be moving out nearly at the speed of light from the center of that galaxy? Well, a black hole could certainly accelerate particles to those speeds, and sure enough, there should be a black hole at the center of this galaxy. M87 is a much larger galaxy than our own Milky Way, and as it turns out, M87 is a much larger black hole than our own Sagittarius A star. More recently, we've had a totally different way of detecting black holes. Going back to the stellar mass of black holes instead of the supermassive black holes, and that's another way to detect them directly by using gravitational waves. This is from LIGO, and the LIGO Virgo are the 2 gravitational wave detectors that have caught 2 black holes falling in towards one another. Those are the blue circles up near the top, both the original black holes that fell in towards one another and the measurement of the resulting mass that would be left over. You also get to see the other masses of the black holes that we have over here in purple as well. You can compare those to neutron stars, which are not quite as heavy, but we detect in a lot of the same ways as we detect black holes if they happen to also be cannibalizing a partner star. There was that one neutron star merger, and we're not exactly sure what that measurement is. This one is, sorry, that one's a little bit less reliable. This one could maybe be a black hole, could maybe be a neutron star. The jury is still out. But it's another fun way to detect black holes. Now, of course, we know that we've taken a direct image of a black hole. So how would you go about doing that? Is it an easy thing to do? Well, if it was, we would have done it already. The big problem is that pretty much every black hole we see is one of 2 things. It's relatively small. Remember, Cygnus X1, 10 times the mass of our sun, just 44 kilometers is its radius, so less than 100 kilometers wide. That's tiny when you're at so many light years away, or so many thousands of light years away, I should say. So they're either relatively small, like a stellar massive black hole would be, or they are incredibly, incredibly far away, like in the centers of distant galaxies. Or they might be both, so it's not a very easy thing to do. How big would it appear if you were to look at one in the sky? Well, we could fix one of those problems. Let's take the closest black hole that we know about. It's about 3,000 light years away. It's, again, something like 10 times the mass of our own sun. Taking its Schwarzschild radius and computing that into an angular size, how big it should appear in the sky, well, it's 0.00043 micro arcseconds. Again, micro arcsecond is a millionth of an arcsecond. That's unreasonably tiny. So, okay, maybe getting a close black hole isn't going to work very well. So we should go for a bigger black hole that might be farther away. And that could potentially work. We know there's a pretty big black hole, and it's far away still, about 25,000 light years away, or 27,000 light years away at the center of our own galaxy. But it's way bigger, 4 million times the mass of our sun. Its angular size, its Schwarzschild radius, I'm saying angular size, but I did the calculation using the Schwarzschild radius, so it would be twice that. But about 20 micro arcseconds for its radius, so maybe 40 to 50 micro arcseconds wide in total. Or you could look at M87. Let's go for the biggest black hole we know about. That's not unreasonably far away. It is it is about 55 million light years away, and that's 6.5 billion solar masses, by the way. We know that now. It was between 3 and 7 billion solar masses before. But that would be just a little bit smaller than Sagittarius A star. So those are two numbers. We're talking about 10s, 20 of micro arcseconds for the sizes of a black hole that it would appear in the sky. How are you able to see that? And this is the equation that Jerry used earlier. If you have a telescope, the angular resolution that you can see depends on the wavelength of light you're using and the size of your telescope. So if you want to see something really, really, really small, like a few or 10 micro arcseconds, you either need a really, really big telescope, or you need a really, really small wavelength of light. Well, which one of these would work for a black hole? One thing that we're limited by is if we want a big telescope, it's easier to build big telescopes on the ground, and that limits, of course, what light we're actually able to see. So that means other than radio, visible light, radio, and other select wavelengths, we're going to have a hard time seeing anything. If we wanted to use X-rays, for example, we have to put a satellite in space. That would get us at the shortest wavelengths, but it's really hard and really expensive to build a big X-ray telescope, so that might be difficult. There's a whole other problem. This is what most active black holes are expected to look like. It's a fun little cartoon of what's going around a black hole and what's going on near a supermassive black hole at the center of a galaxy if it's eating stuff like, for example, M87 is. You have an accretion disk around the black hole. You can have jets of relativistic charged particles moving away from the black hole. Outside of this accretion disk, you'd also have a large dusty torus, so even to be able to see in towards the center, you need to be looking at the black hole from the right angle. On top of that, there's all this other gas and other dust that can be floating around, changing the light that we see. So they can be pretty much putting out light at all these different wavelengths, infrared, visible, ultraviolet, or in the X-rays if you get closer and closer towards the center, as well as a whole host of different radio wavelengths as well. But again, what we want to try and see is coming right near the black hole itself instead of seeing all of the rest of this other stuff. And there's only certain wavelengths that will work for that. This is a video I found actually earlier today because I was trying to come up with a good way to explain it, and lo and behold, the Event Horizon Telescope made a video that does a perfect job. But if you look at the wavelength of light, we're going to start with 3 millimeters, 30 millimeters, and we're going to get into smaller and smaller wavelengths and see what a black hole would look like. If it's an active black hole, it means there's an accretion disk around it, there's stuff falling in towards the black hole, and there's jets flying out. We don't want to see any of that stuff because we want to see right down to the black hole itself. If you change the wavelength and make it shorter and shorter and shorter, you're able to see closer and closer in towards the black hole. These are the wavelengths of light that would actually be passed straight through that surrounding material. And we just passed the 1.3 millimeter wavelength that the Event Horizon Telescope used, so I'm going to play this again, going from 30 millimeters in wavelength down to very tiny numbers in wavelength. And hopefully it reloads. Let's see if I can go back. There we go. So again, this is 20, now 10 millimeters, 987, and right around the 1.3. Maybe I can even pause it if I'm quick enough. Oh, pretty good. All right, 1.2, we'll take that. You actually get to see right down to the black hole. You get to see its shadow. You might still get some of the jet coming out as well. But this is the wavelength that it turns out is actually going to be the best for being able to actually visibly see the black hole as opposed to all of the other stuff going around it. So that means we're stuck with our wavelength. Then our only solution to get good enough resolution to see a black hole, we're stuck with building a bigger telescope. And how big, you already know, but of course we don't have an Earth-sized telescope. Like Jerry talked about earlier, we have lots of pretty big telescopes all around the world. And the way to put them together is called interferometry. When you're using radio waves, different wave fronts come in, and if those waves are in phase, they can add together, causing constructive interference where the waves appear twice as tall, or the signal appears twice as strong. Or if they're exactly out of phase, you could see no signal at all. Since these, if you have radio dishes at different positions, they're going to catch the waves coming in at different points of those wave fronts. So they can be in phase or out of phase, and basically by combining how strong the signal is and how strong those different how out of phase those different telescopes are, you can sort of link together these telescopes to provide a better image. It's something that's done not just in astronomy but in other fields as well. There are lots of places on Earth where you have just lots of dishes that are already combined together. ALMA is a great example. It's one of the 8 telescopes in the Event Horizon Telescope. But you have these 66 dishes in ALMA. Their maximum baseline, if you spread them, drive them all the way apart as far as they can away from one another, the maximum baseline would be 16 kilometers. So it's a huge area that they have over there on that plateau, which is a pretty big baseline. But when you're linking together telescopes, your angular resolution is your wavelength divided by your baseline. So the bigger baseline you get, the smaller angular resolution you have. So you'd want to have these telescopes as far away as possible from one another. There's one in the United States, which would be a little bit easier to visit. It's the Very Large Array. This is not one of the Event Horizon telescopes. But with 27 dishes, you can have a maximum baseline of 36 kilometers. Those can work together to be like a 36-kilometer wide dish. It works for arrays like this that are all in one locale, but the principle is the same if you just put dishes in different places on Earth. And that's exactly what the Event Horizon Telescope did. They had to use certain types of dishes, so not every radio telescope would work. But these are the 8 different Event Horizon telescopes and the lines drawn in between them as well. This is another image of them. So by putting all of these stations together around the globe and calibrating them just so much that you know which part of that wavelength of light, which part of that phase you're getting the light in, you can use these together as a giant telescope. We also have another really, really helpful hint. Every time you add a new telescope, you can draw a line between that telescope and every other one of the telescopes in your array. So with 8 telescopes, we have 7 plus 6 plus 5 plus 4 plus 3 plus 2 plus 1 different baselines that you have that add together. And each baseline shows up as a point as what we call the UV plane. If you're doing radio astronomy, the UV plane is like the Fourier transform of your image, but that's where you're actually able to take measurements of what it is that you're looking at. So each one of those different colored sort of curves on this chart is a link between 2 of the different Event Horizon telescopes. Now the reason that they're not individual points is because the Earth helps us out. The Earth actually rotates. And as the Earth rotates, that sort of sweeps out part of our baseline. So instead of just having individual points, letting the Earth rotate around for us sort of changes the picture of what our telescope is actually able to see, which is pretty useful. So again, that's why we have those curves all the way around. If you're looking really closely at these names, you might notice, I think the South Pole Telescope is not in this image. Unfortunately, the South Pole Telescope didn't actually contribute to the image itself, but it was extremely useful in calibration for the whole Event Horizon Telescope. M87 was not above the horizon at the South Pole when they took that, when they took the image back in April 2017. Putting all these together, you're actually able to get together an image. Now, I've just gone from showing you a picture of the telescopes to the image, and there's an incredible amount of work and some incredible stories that goes into not just the data that they had to take to be able to do this, or the incredible timing resolution of all the atomic clocks that they had to synchronize between all of the different telescopes. I think my favorite story, though, is the internet is too slow to actually transfer the data between any of the telescopes. To actually be able to process it, they had to literally fly hard drives in between the different locations.
Yeah.
And it was April 2017 when they took the image. This is for the April 11th night of observing. The South Pole Telescope is experiencing its winter at that point, and it's basically closed to flying. So they didn't actually get to fly the South Pole Telescope data until 6 months after they made the observation. Everybody was just waiting around for those hard drives to show up via plane, which was a pretty crazy story. They took several different nights of observing throughout that 10 days or so, where they actually had these. It was 10 days in April that they were able to take these, and they actually put together different images for each of these nights. The black hole itself, because it's a giant black hole, it doesn't actually change that quickly. If you imagine dropping a particle in and around an orbit around that black hole, right outside, say, its Schwarzschild Radius around the event horizon, it takes about 2 days to go around. Again, this black hole is bigger than our solar system, so 2 days is really fast to get all the way around. But because it's such a huge black hole, it doesn't change quickly. It can change dramatically over long periods of time. If you look at stellar mass black holes, those can look different depending on the night you take an observation. Those change rapidly over time, but with a huge black hole, its timescales are shorter. So they did take pictures for every single night because they knew it might change ever so slightly differently over these nights. This is back to the April 2017 one. And I do want to say one of the first things is it's a direct image of a black hole, but it's not, of course, invisible light at 1 or 1.3 millimeters. So a lot of people would ask me after this happened, why does it look orange? Why does it look red? Is that really the color that a black hole should be? Of course, it's not a color at all. We just false colored the image. It's a brightness scale. So the yellower or whiter or lighter orange that it looks just means that we're getting more intense light from that point around the black hole. So it's a false color image, which is just something I should say, and it's measuring brightness at each little point around our image. So then the other question is, what are we actually seeing? What does this mean? You might have guessed that that might be what a black hole looks like, but it's sort of a complicated thing what a black hole really should look like. This shadow at the center is the shadow of the event horizon. So that little hole in the center of your black hole donut, that's sort of the ka-ching, that's the black hole. That shadow shouldn't be there if there wasn't an event horizon. This ring of light that we see around it, and that ring shape is exactly as predicted as it should be, not necessarily, I mean, a black hole is spherical, but not necessarily because of that, more because any light leaving near this black hole, its path of travel is so warped by the gravity of the black hole that it will form, any light that gets to us should form a ring around the black hole, which is exactly what you're seeing. Now, it's not a perfectly symmetrical ring either. There's that brighter part on the bottom, the darker part on the top, and I'll talk about that in just a moment, but I want to just bring up sort of the photon sphere is that ring of light that we see. If you just shoot a flashlight at a black hole or shoot a bunch of different laser pointers at a black hole, these are the different paths of travel. The blue that we see, it would be light that's gotten too close to the black hole and will eventually inspiral and fall in. If you're exactly on the photon sphere, sort of the crazy idea is if you could physically stand on this, right at the radius, it's about 1.5 Schwarzschild radii away from the black hole, just outside the event horizon where you get the photon ring. If you were to shine a light just in one direction, that light would illuminate the back of your head, and the light leaving the back of your head would come right back around the black hole, and you'd be looking at the back of your head, standing there at the black hole, which is just a crazy concept to imagine, but still pretty awesome. It's light just outside of that, so this red arrow here, just outside of the photon ring, that goes around the black hole, and then is free to escape, come all the way to Earth, 55 million, 6.5 billion. Is the mass of the black hole, but 55 million light years away. So this red photon went around the black hole, traveled through space, through the dust in the center of that galaxy, all the way out through the surrounding chaotic environment of that black hole, through the intergalactic space, 55 million light years, to our detectors at those 8 event horizon telescopes here on Earth for us to be able to see that ring. This is that 1.5 Schwarzschild radius I said for the photon ring. It turns out that's just for a non-spinning black hole, but black holes we expect to spin. Most measurements we have of the spin show that they're spinning really, really quickly. Most things in space are rotating, so that shouldn't be too much of a surprise. But it depends on how quickly the black hole is spinning that exactly where you see that ring. Going back to this, again, this is this little dot out here that I should have talked about earlier is the angular resolution. That's the 20 microarcseconds of the Event Horizon Telescope. So it's a really, really, really blurry picture, but it matches exactly what we'd expect if we had a perfect resolution to see the black hole. These are magnetohydrodynamic simulations of trying to take into account what the magnetic field around the black hole should be like, which will depend on how quickly it's spinning and its surrounding environment. Following particles falling in towards the black hole, tracking the travel paths of the light bending around the black hole as it leaves those particles to come back to us so that we can detect it. These are the simulations that we get from running them in our supercomputers. This A number shows how much the spin affects it. So this is a really fast black hole. This is a non-spinning black hole. This is material that's moving in the opposite direction for the way that the black hole is spinning. But each of these look pretty similar to our sort of fuzzy image. The best match is probably a black hole that's spinning really, really quickly, and the stuff falling into it spins the same way. The other fun sort of thing that you can do is just by taking a ruler, or like a meter stick, and sticking it against that shadow at the center and measuring how far away that shadow is. That number is directly related to the Schwarzschild radius for the black hole. That Schwarzschild radius for the black hole depends distinctly on its mass. And so just by taking this image, it's a direct measurement of the black hole mass. And measuring black hole masses is a really difficult thing to do. By sort of following stars that go around the black hole, as well as by following hot gas that flows around the black hole, we had 2 separate measurements, right around 3 billion solar masses and right around 6 billion solar masses. And we weren't sure which one was right. Now we have a direct measurement of 6.5 billion masses for the mass of the black hole. That was not possible before. So just by having this image, we suddenly don't have to ask the stuff flying around the black hole what the black hole looks like. We can just look at the black hole ourselves and take direct measurements. And we can also further test general relativity. If it wasn't a sphere, but it looked totally different, that might mean that there's something going on in this extreme gravity environment that doesn't follow general relativity in the way that everything else that we've measured does. So it's a way to test predictions of general relativity directly as well. And now, if you add in LIGO, which was the other direct measurement of black holes that we had before, it means that we're measuring black holes that are over 8 orders of magnitude different in scale. Those LIGO black holes right around 50 solar masses to now something that's 6.5 billion solar masses. And the physics, as it works out, is the same, despite the crazy difference in scale. And the best way to finish it is to look at a video that the Event Horizon Telescope took themselves, or made themselves, where we can go from our Event Horizon Array, we can look out in the constellation of Virgo, which is the direction you have to look to see the galaxy M87. And if we zoom in, you'll actually be able to see that fuzzy point of light at the center suddenly look like a galaxy. It won't take long until you see a jet of material coming away from the center of this fuzzy galaxy here, as we're getting just now into the galaxy itself. There's that jet that you can see of relativistic particles leaving the black hole. If we get in towards the center of that galaxy closer and closer, at different radio wavelengths, we peer through different parts of the accretion disk until we get to the one wavelength where we get to see right down to the center. And that's my talk. Thank you guys so much.
One fixed question. That shot of matter that's coming off, that's not coming from inside the black hole, because obviously the black hole can't get out of there.
Exactly. You're absolutely right.
So tell us what that is.
The stuff that has fallen into the black hole is still emitting light, but it's not getting to us. That's the shadow that we see. If the light was able to escape, it'd be brightest at the center.
What is that going to like? That's not,
That beam of light comes out towards us in our general direction, and then the gravity of the black hole pulls it right back in.
back in. Okay,
Yep.
but it doesn't escape the black hole, it escapes around it, right?
So yeah, you'll have some you'll have material that's around the black hole, which can then emit light that escapes, but
I got
once you cross inside, when you're inside the photon ring,
We're done.
those photons travel in a circle. Particles can't actually stay at that stable orbit, so any material would have already fallen in. And once you get past the event horizon itself, that's when any light that you leave won't just go in orbit around the black hole, you can shine it straight out, and it won't be able to escape. That shadow is about 2 times the actual Schwarzschild. The radius of that shadow is about 2 times
Cool.
the actual Schwarzschild radius, because there's a little bit of a space where you can't have light escape even still. Yes?
Does the ability to directly measure this black hole help us calibrate the observations of captured stars orbiting black holes in other environments where we can't directly see the black hole?
Absolutely. We feel pretty good about if we can see stars in orbit around a black hole, it's a pretty direct measurement of its mass. This one we get to measure its size to tell us a direct measurement of its mass. Those 2 different mass measurements we had for this black hole before a month ago were dependent on 2 different things: hot gas spiraling around the black hole and stars that are in the vicinity of the center of this galaxy. And it turns out the star method is a lot better. A lot of other black holes we know the measurements of, or we have good estimates of the mass. When I say good, it's really tricky to measure the mass of a black hole, so like give or take a half at least. But a lot of the other measurements we have, they're probably half of what they should be, what the actual masses of the black hole are. And this is the first way we get sort of a look into how wrong we are with some of our different measurements of the black hole mass. Yes?
2 questions, if I may. When I look at the picture, it's brighter on the bottom than the top. Why is that?
I meant to mention that, so thank you for bringing it up. So this material is spinning around the black hole, and the direction that it spins, the orientation that it spins, will affect how it looks. Now, the reason it looks brighter when the material is coming towards you, and it looks fainter when the material is moving away from you. The reason for that is called relativistic beaming. The light, or the material that emitted this light that's going this way around the black hole, when it's coming towards us and it's emitting light, it's moving relativistically. So if it shoots a photon out, we catch that photon, but it's moved towards us and it's closer and it's shot another photon out. So for every hour you look at this section of the black hole as that material is coming towards you, you're actually catching, because it's gotten so much closer to you in that time, you're seeing more than an hour's worth of light coming from that side in the frame of the stuff that was moving in that direction. The stuff that's moving away from you, it's gotten further away. So if you observe it for an hour, in the frame of the stuff moving away from you, it was only maybe 5 minutes of light. So it looks much dimmer when stuff is moving relativistically away from you, and much brighter when stuff is moving relativistically towards you. And so we get the brighter part of the ring when that material is coming around. So they say it's orbiting clockwise. The black hole is spinning clockwise, the material falling into it is also going around clockwise, and that it's sort of, the axis of rotation is pointing away from us. So I have to struggle with my right hand and try to get my thumb to point in the right direction, but that would be why. So your second question?
Is the image looks lumpy.
Yes,
I see at least 2, maybe 3 bright spots.
absolutely. And I think those lumps change between the different images you take on different nights. At this point where the black hole is, it's pretty chaotic, and even though it changes only over, several hours to a day, this material, right as it's about to fall into the black hole, isn't following a perfect path or staying perfectly in the disk. So those brighter spots you get, you just had to have a clump that was traveling in that direction and producing that light that we see. So that clumpiness would and sort of should happen. Another effect of that clumpiness is just sort of the poor resolution that we have. I would have to go back to those sort of, if we had a perfect view, what the simulations would show us, would look a little bit less clumpy, but you'd see certainly strings of material as emitting light as they fall, as that material falls in. Yes?
What's the order of magnitude of how many solar masses falls in per day, say?
It's really slow. There's not a whole lot. This black hole is sort of gorging material from around it, and I think we're still probably some fraction of a solar mass per year, if not several solar masses per year. So on the order of it, it's pretty slow. black hole isn't growing appreciably in size in a human lifetime or most massive stars' lifetimes, but over maybe the age of the universe, it might have gotten quite a bit heftier eating material that quickly.
Thank you.
Yes?
How close or how far away is Earth from a black hole?
So the closest one we know about, 3,000 light years away. And
That's not very much.
no, it's not very well. You can think of it a couple different ways, right? So black holes get this really bad rap in science fiction where they're just going through the galaxy, eating up everything. And we're looking at a black hole that's devouring all of the gas from within its within the center of its galaxy, and it's an outrageously energetic process. The stuff that falls out of its mouth that it doesn't eat is that jet that extends several thousand light years out into the rest of the galaxy. And we actually think black holes can have a huge impact on how the rest of the galaxy around it lives and evolves over time. But you can also think about it this way. The closest one to us, 3,000 light years away, even if it was traveling relativistically, we've got 3,000 years to have to worry about it. The other good thing, though, is that most black holes, being the heaviest thing around, don't really move that much. It's just other stuff that moves around them. So the sort of way to be safe in space is you don't have to worry about a black hole unless you decide to fly right at it and get too close. And then it would be sort of maybe not such a good thing for you. Yep. But yeah, our solar system certainly is safe. I think the chances of a renegade star flying through our solar system are higher than a black hole ever coming near us, which is a pretty good thing.
Is there an estimated count for the number of black holes in the Milky Way?
We have detected under 100, and we think that's less than 1%. There's certainly thousands, if not tens of thousands, hundreds of thousands in our Milky Way. We're not, the guess point is what percentage of them have we actually detected. That Cygnus X1, which is one of the first ones we detected, it's cannibalizing its partner star. Well, that means that those are two stars orbiting one another, and the heavier of those stars went supernova, collapsed into a black hole, and its friend decided to stick around through that supernova, wasn't blown away, and stay close enough that it can accrete material onto that black hole. Most supernova simulations would show that that would give a pretty strong kick to your partner star. So it's only a tiny fraction of black holes that, even if they're close enough to their partner, would be able to start cannibalizing their partner. And we've actually seen black holes turn off and turn on again. We discover new black holes when they randomly turn on and we didn't know that they were there. It's a thing that regularly happens, and we're only seeing a small fraction of the ones that we expect are in the Milky Way. But Milky Way is a big place, so they're all over us. Yes?
I was watching actually a documentary last night on TV about the black hole, and the scientists that were running the computer program that actually saw it. And to me it was amazing, as you said, the amount of tetrabytes of data they had captured in the process. They must have one heck of a computer to process all that data.
Yeah, they really do. It's you could almost fill the room with the hard drives that they had just for this, and those are the newest steady-state hard drives that they've got. So I forget if it set records or anything like that. The atomic clocks they have might have set records for precision, and the data recording might have come close to setting records, but I think folks at the LHC have them beat in terms of total amount of data when they're running that thing just constantly. But yeah, it's a pretty crazy story now. I haven't, can you tell me what that documentary was? Because I'd probably like to watch it.
It was just last night on TV. It was about an hour and a half long show.
Okay.
I just have to catch it. I didn't catch the very beginning. I caught it about maybe halfway through.
Gotcha.
It was an actually an awesome show because showed all the, gave a pretty good explanation of how it works and the process they're doing. You could see it in real time when they were actually looking at the results they were getting back, and they processed several of these, and you could see the image, I guess, sharpening or doing the various transforms, and all of a sudden there it was. They just went bananas.
Yep. The imaging algorithms alone are pretty incredible. But yeah, I heard a story from the guy who gave most of the press conferences, the leader for the Event Horizon Telescope. That first sort of collection where someone sort of like sneakily passed him what they had gotten so far. We know this isn't even close to being clean yet. This is a really rough look at our data. It looks like a ring. And he just, he wanted to jump around and scream and lose his mind. It was pretty cool. So.
All right.
Yeah. Do you know do they know anything about the star that became the black hole? What type of star it was?
That's a great question. Forming a black hole that's 6.5 billion times the mass of our sun in the age of our universe is unlikely to happen from the death of a normal star. even if you had like a star like Cygnus X1 that's cannibalizing another giant star, well, even if it eats the entirety of its partner star, it's only maybe 20 solar masses. So to get something like that, you need a whole different game. And we're still trying to figure out where those black holes come from. The ideas are super dense part in the super dense sort of hole from the very start of the from the Big Bang, collecting a ton of material right around the time or before the time of we get to see the cosmic microwave background. You've got sort of a seed for a black hole already there. Or the very first population of stars, you might have had just clouds of gas collecting on themselves that were orders of magnitude too heavy to ever be stable as a star, and it just instantly collapsed. No star, no supernova, nothing, right into a black hole like that. And we think another one of the ways that they get bigger is eating each other, merging. We've found galaxies with 2 supermassive black holes at their center, orbiting one another. It's not crazy to think that M87 probably ate several galaxies, and those black holes from those galaxies fell into this guy. Yes?
I'm sorry, we
Okay,
have to
sorry.
get out of here. So, thanks very much, Ben.
If you have more questions for Ben, he gives presentations at the Wayne State Planetarium Fridays. Not every Friday, but he's there a lot, so bother him.